Okay, so maybe I'll resume. Okay, so I said at the end of the first hour that we are specialized to the case of complex number. If I look at a parameter which is of good parity, then it is nothing but a map from, it will be a bunch of, it's a sum of even dimensional irreducible representation of SL2. Okay? And so actually, this type of parameters are also called unipotent. So maybe I make a formal definition. In general, right? So if so F is equals to real or C, and another parameter is said to be unipotent if the restriction to WC is trivial. So in particular, so here note that, in the case when F is real, the Weil group of real numbers contains C cross, right, as a subgroup of finite index, of index 2, okay, and quotient can be thought of as the Galois group of C over R. Okay? So if you have psi, if it is restriction to this part is trivial, then say unipotent. Okay, so in the case of, okay, and then you can consider the set of, for a given group G, you can look at the set of unipotent parameters. Okay? So what we are saying here is that if F is equals to C, then in fact, the set of good parity parameters is just the same as the unipotent ones. Okay? But for when F is real numbers, it will not be the case. Okay, so so in this case, it turns out that so if I take a good parity G, then Babesh and Vaughan already in A5 they have already defined, constructed a packet so let me decorate it with a BV for Babesh-Vaughan attached to psi. Okay. So what is their definition or construction? Okay, so to describe that, need to set up need to introduce something. Okay, so we are simply looking at. Yeah, I'm assuming F equals to C. So in my example, so my good parity parameter is just a map like that. Okay, and of course you can have the associated map on Lie algebras, right? This is my group G, let's say. So this Lie algebra. Then you can look at this element, maybe half of d psi of 1 minus 1, 0. Okay, these are trace 0, 2 by 2 matrices. Maybe I shouldn't, no, this is not G, this is G hat. So we call it G hat. Now, of course, there's no harm, because you can conjugate this thing. You may assume that it lives inside some Cartan subalgebra, inside some torus, okay, in the torus subalgebra. Now, and on the level of a torus, the Lie algebra of the dual torus is identified with the dual space of a Cartan psi algebra in G. Okay. And okay, so anyhow, I get an element in here. Of course, should I? No, I'm happy to just leave it like that. Okay. Now, of course, as I said, I can conjugate this element around. So I'm going to think of this element. So I get an element inside this, but it is you know, kind of well defined up to the vowel orbit because I could have conjugated my guys around. Okay. Even if I insist that the diagonal elements in SL2C goes to a particular thing here, I still have the freedom of conjugating by the vowel group. Okay, so I'll get an element here, and you see an element here. Okay, so I want to say this gives an infinitesimal character. Lambda psi, comma lambda psi in H star cross H star. So this is an infinitesimal character for GC. An infinitesimal character is usually you have a same Rayleigh group. You can look at the Lie algebra. You can complexify the Lie algebra. You can look at the universal enveloping algebra. It has a center, okay, and Harishchandra described that center, and from that, so the description is very similar to the Sataki isomorphism in p-adic groups, and you see that infinitesimal character will be an element in H star. Okay, but because now we have a complex group, we can think of it as a Rayleigh group, right? So when we take its Rayleigh algebra and complexify, we're going to get two copies of the Lie algebra of G. Hence the doubling here. Okay, okay, so it doesn't matter. The point was just that if you give me an A parameter, I get an infinitesimal character. Okay. The other thing I get is, of course, a map from here to there. It gives me a unipotent conjugacy class in SP2M, okay, by the Jacobson-Morozov. Or if you wish, just take the image of 1101 in there. And similarly on the Lie algebra level, take the image of 0100. And, okay, now, because of the form of our parameters, all these di being even, okay, so let me see. So we get an infinitesimal character, but psi also gives us a unipotent element, okay? Nilpotent element, or if you wish, nilpotent conjugacy class in G hat. Now, as I said, because of this even assumption, you know, you get a nilpotent conjugacy class by considering any maps like that. Okay, but our maps have some special condition. Okay, this condition implies that the nilpotent element is called special in the sense of lustig. Okay, never mind what it is. The point is that there is a bijection. This is due to Lustig and Spottenstein between special nilpotent orbits on G and special nilpotent orbits on. So we get a certain class here. I'm going to call that class O hat psi. The hat reminds me that I'm on this side. So under this, bidirectionally correspond to some guy there. So for example, if this were like a regular orbit, this would become the zero orbit. So it's kind of a big to small thing. Okay. Now, all right. So so to summarize, we start with a parameter of that of good parity. We get a few things out of it. Okay, namely this infinitesimal character, and then we get these two orbits here. Okay. So now what Babesh and Vaughan consider was that they considered a set of irreducible representation of G. Okay, G is this complex group. Okay, with the following two conditions. The infinitesimal character of pi is that one. Okay, the one that we have. And the second one is that the wavefront set of pi is this orbit. So, sorry? Yeah, so the wavefront set is an invariant that you can define for any, say, irreducible representation. Yes, I guess so I don't know if this is equivalent to being special, but things with this property will give a special orbit, special Unipotent orbit. And the point of wanting special is because I want to come to this side. Yeah, and then after I come to this side, I can make this assertion. So I will not define this, I will not give the definition of wavefront representation, but it is some, this is a variety, right, that measures the size of pi. So if pi were generic, i.e. has Whittaker model, then the wavefront is going to be the principal, the regular Unipotent orbit. If pi were trivial, this would be the zero orbit. Okay, so the larger this thing is, you should think the bigger pi is. Okay, so you can define this, that's not a problem, but the question is, of course, they show something about it, right? So what did they show? Yeah, so I should say that, of course, it's kind of reasonable to look at this, and there could be many other representations that satisfy this second condition with different infinitesimal character, and in some sense, this is the smallest one, meaning closest, the shortest length, so to speak. Okay. I should take closure. Okay, I should take closure. Okay, so they look at this set. Now, what did they show? They show, of course, they were motivated by Arthur's conjectures, which was just beginning to come out in the mid-80s. Okay. They show that any pi in there is unitary. Firstly, which is good because Arthur packets are supposed to contain unitary representations. So, okay. Sorry? The group is classical. No, here they actually do it in general, I think. Yeah, they do this in general. But in my talk, I'm just taking G to be SO2n plus 1. Okay, so then they give a parameterization. You see, this set is by definition multiplicity free because by definition it's a bunch of irreducible representations satisfying some condition. Okay. They show that there's a natural bijection between this set and irreducible character of a certain component group, which, okay, so I will now decorate a little bit. So this is a Lustig's quotient, so to speak, of so actually this is, I'm skipping some things here because what they actually show is that they show that this is in bijection with the component group of this O side, and then the Lustig quotient of that. Okay, in some sense, they are not really working on the dual side. Okay, they're not working on the parameter side. They are all working on the group side. You have this orbit. Okay, you can look at the component group. Okay, there's a certain quotient that Lustig singled out in his studies of representations of finite reductive groups. Okay, and then what they have is this. Okay, but because of the properties of this bijection, you have a kind of identification of that. Okay, which needs to be explicated, of course. Okay, so you have that, and finally they verify this endoscopic character identity. Okay, because in some sense the way that you can define this packet, but now you want to understand what are the things inside there. And what they did was they managed to, so basically you want to classify things with this property. And what they managed to do is they managed to find the characters of this guy as a linear combination of the characters of standard modules. In other words, they write the character of these guys as a linear combination of characters of induced representation. Okay? And characters of induced representation are quite easy to induce from Borel, by the way. So they are quite easy to write down. Okay? So, and it's because of this they were able to verify that. Okay? All right, so that's that. But they didn't show the twisted one, the one to GL. So in Moglen and Reynard's paper, they have to check that. They have to explicate this, for example. Okay? So in some sense, maybe you can say it's reinterpreting some of their work from the point of view of Arthur. Okay, so yeah, so this Lustig quotient will be a quotient of the one that we are considering. So it means that this is a smaller set of irreducible characters, right? Which means that those characters that doesn't factor through the Lustig quotient, they just index 0. So maybe I squeeze it in here. So the theorem of Moglen and Reynard was that they are equal. Okay. Okay, and actually they say a lot. You may ask, the local Langlands correspondence for complex group is known. I mean, for Archimedean case, right? Local Langlands is known. So you may ask, so what are the Langlands parameters of the representations in here? So they also wrote it down. So, and I actually wrote it down here, but I think maybe I won't, this is going to take a long time to write them down. Okay, it's very intricate, so maybe there's not much point. Okay, so they actually wrote it down. Okay, and what else can I say? Okay, I wanted to say also that paper of Barbash from maybe 3 years ago. So come over here. Give another perspective on this A packet that he defined with Vaughan. Okay, so let me see that, Barbash. This is 2016 maybe. Okay. Now this is in the House 70th proceedings. So what he did here was like he showed that elements in here can be constructed as sort of iterated data leaf. Anyhow, if you don't know data leaf, then no point for you just ignore this. Okay. So the point I want to say was that there are various ways of understanding this set, right? Already from a long time ago, they simply define or describe this set satisfying some very simple condition. Okay, this is not very explicit, right? Because you write like that. Who knows? Is it empty? I mean, how many there are, and so on. Okay, but they actually understand a lot. They could write down these representations They can write down the Langlands parameter. Okay, they can also express their characters as linear combinations of characters of standard modules. Okay, hence they understand their character theory very well. And in addition, they can be constructed by using these data liftings as well. Okay, so that's so in that sense, we understand everything about sort of local A packets over complex numbers. Okay, because general case can be reduced to good parity. Good parity, basically their work. Okay, and also supplementary work of Moglen and Renard, so at this stage, by inspection, we observe that complex A packets are multiplicity free. Okay, because these guys vis-a-vis are, and once you know they are, when you induce, you check that they are. You don't create new multiplicities. Okay, so by inspection. Okay, I want to come to the real case. In the remainder of the time, I want to talk about the real case because it will be slightly more complicated than the complex case. Okay? Well, we already have one reduction, right, from general parameters to the one with good parity. What does a good parity A parameter looks like in the real case? Well, in the real case, okay, so in general parameter, okay, you can think of it as a 2n dimension representation. It will break into pieces. So each of the pieces will be a tensor product of an irreducible representation of the Weil group with a irreducible representation of SL2. So we know what irreducible representation of the Weil group of R looks like. They are either one-dimension characters or 2 dimensions, okay, as described in Lei's talk. So let me write the two parts separately. Okay, so this is the part where you have the 2 dimension. Okay, so these are 2-dimension irreducible representations of the Weil group of R. Okay, so refer to Lei's talk for what they mean. So they correspond to discrete series representations pi ki, let's say, of GL2R. Okay, so that's the part where this is 2 dimension. Then you have the part where this is 1 dimension. Okay. Okay, so let's write chi j. So in general, A parameter will look like that. Okay, but you want it to be symplectic, right? Because this take value in SP2n. Let me see. Sorry, we are already assuming this is good parity, right? Because I already reduced that case. So this means that every summand here is supposed to be a symplectic representation. What it means for this is that the BI has to be even and chi has to be a quadratic character. Okay. Well, of course, the Weil group of R has 2 quadratic characters, okay, either the trivial or the sign character. So chi j is either trivial or sign. Now, what about this part? Let me think for 1 second. So I guess this is sometimes symplectic, sometimes orthogonal, maybe depending on the parity of the, the highest weight, the lowest weight, or something like that, depending on the parity of this. And then this has to be of the right parity so that the tensor product is symplectic, okay? Which means that if this is orthogonal, this has to be symplectic, and the other way as well. Okay? So you can write it down, so let's not spend much time on it. So in general, it will look something like that. And I need each summand to be symplectic. Okay, now, so you see that the shape is more complicated than a complex case, right? Because in a complex case, it was just representation of SL2C. Okay, so here we have more, there are more degrees of freedom, so to speak. Okay, so this motivates us to define the following. So I guess it is natural to say that, well, if you want something that looks as close to the complex case as possible, maybe you just kill this part. Okay, you look at the parameters where this part is not there. Okay, but of course you are missing maybe what you think might be the more important things because of this discrete series representation. So you may also look at things which doesn't have this part. Okay, so there are various subsets of the good parity that you can define. Okay, so we are going to I'm going to write down some subsets. Okay, so we're going to consider the chain of containment. So I have the good parity part. Here I'm going to write, let me just write a very regular. And then I have unipotent. Okay, I've already defined this, right? So unipotent just means that psi restricted to WC is trivial. Okay? Which means that this part is gone. So this is the part that most like the complex case, right? In a complex case, we say that unipotent and good parity are the same thing. But in real case, they are not. Okay. Okay. No, this is I. I is empty. Okay. Now, you may also look at, roughly speaking, the set where J is empty. Okay, so this is, what is this? This AJ stands for Adams Johnson. And what does it mean? What is the requirement here? Basically, J is empty, so but maybe not completely. At most one term. At most one term. But you should morally think that I want J to be empty. Okay, so this lecture is split into these two parts. What does a very regular means? It means that when you look at this, there are these KIs here. You can arrange them to be in decreasing order without loss of generality. Okay? So K1 bigger than equals to K2, bigger equals to K3, and so on. But I would like this to be much, much bigger than that. In other words, I want them to be big and very different from each other. So let's say the last one is KR. Okay, so some condition. Some condition like that. And you can explicate this, but let me not do it, okay? We just want to get a sense of what it involves. It means that those guys have nothing to do with each other, just very far apart from each other. Okay. Yeah, so actually there's an intersection, right, of these two parts. The intersection of these two guys are basically the packets that correspond to one-dimensional representations. We call that a trivial representation, for example. Okay. All right, then. Okay, so anyhow, we have this picture. So it's a V for very regular. Okay, so and what Moglen and Renat did was to do a successive reduction. So we already go from here to there, right? And what was used in this reduction was parabolic induction. Right? We simply say that if you know this, then everything else can be obtained by ordinary parabolic induction. They will always induce irreducibly, and so on. Okay? So we would like to reduce further from here to there, there to there, and so on. Now, of course, you can start from this end or you can start from this end. Let me start from the bottom. Yeah, let me start from the bottom. Okay. So you see there are several steps. So first we can say, can you understand this? Okay. So the unipotent parameters. Okay, so this was understood in some sense by Glenn in her paper in the same some proceedings of someone's birthday conference. I forgot who precisely. Okay, so what she showed there. So now I will, last half an hour, I will just give some rather impressionistic discussion. Okay, so how did she construct these guys? She showed, so Muglen showed that that for psi in here, the Arthur packet, the one associated by Arthur, can be constructed by iterated theta lifting. Okay, that's how she produced this by iterated data lifting. Okay, for those who have worked with data correspondence before, so we are looking at a case where this part is not there. So essentially, it's up to this is a sign. That's all. Okay, a bunch of representations of SL2. So just like in a complex case, except that here now this guy may not be trivial, but it could be a sign. Okay, and what data lift does is the following. So you can, so let's say there are 10 terms here. Okay, in this summand, you can successively peel off one term at a time. Okay, so for example, you take the one with the largest dimension. Okay, you remove it. Of course, you get a parameter of smaller dimension. Okay, and then which comes from a smaller group. There's a way of getting from the bigger group to the smaller group, which is what data lifting is. Okay? This is by data lifting, is certain explicit construction. And what she showed is that so if you give me something with 10 terms here, I can create the representations in this packet as data leaves from a smaller group. So what representations do I use on the smaller groups? They are representations that belong to the Arthur packet whose parameter is this one, but with one of the term removed. Okay? And then you can repeat that. You just keep removing, and finally you are left with one term. And when it is one term, you just have a one-dimensional representation. Okay? So in other words, it can be built as a iterated data leaf from one-dimensional characters, representations of smaller groups. Okay, so in this particular example, where my group was SO2n plus 1, right? What the data leaf connects to is a metaplectic group. Okay, and then you do it again, you come down to a smaller one. So you have this, go all the way down. Okay, you may end up on this side or that side. Okay, so that's how she shows she can construct this packet. So of course, how did she verify that this is the right packet? Well, we say that so far we have said that the only way we have seen to verify that some candidate packet is the right one is to verify these endoscopic character identities. Right? If you try to do that, you would imagine that you have to be able to answer the following question. Okay? If I have a representation here with a certain character, and it comes from data leaf from a representation from a smaller group here, what is the relation of the characters of this guy with the characters there? Okay? You kind of have to be able to know how characters behave under this data leaf. And this actually is not fully known today. It seems to be a hard problem. It's not clear how characters behave under data correspondence. So how then can she check that the local character identities, the endoscopic character identities hold. Because, you know, at the bottom, we are going to start at one dimension, and one dimension is trivial to check. Okay, it's very clear here, right? So we hope to propagate those character identities up. Unfortunately, we don't know how character identities behave under data correspondence. So how did she check that this packet is, that, you know, she defined is the right one? And so the answer is by using global methods. Okay, because you see, these other packets, even though it has a local characterization by character identities, we did say that they are, I mean, the reason for their existence is to serve as a local ingredient for the solution of a natural global problem, the problem of understanding the automorphic discrete spectrum, right? So, in some sense, so what she did was the following. You look at this parameter, right? There's nothing here. So this is a local parameter. But you can globalize this parameter quite easily because you just have to find some, say, for example, a global quadratic character. So you pick a number field, say a real number, totally real number field, for example. Okay, then you, well, let's say Q. Okay, and then you find some quadratic Hacker character of Q with the given localization, because this could be trivial or non-trivial. Right? So you can write down a global parameter, a global unipotent global A parameter. Okay? Actually, actually Mogren studied these global parameters a long time ago, in the early 90s. She calls them quadratic unipotent, because this is not necessarily trivial here, it's a quadratic character. So she had, in the 90s, she had already shown that, I mean, she has a lot of understanding of this, the near equivalence class corresponding to these quadratic unipotent parameters. She knows that she can construct them by global data lift and so on. Okay? In some sense, she could in other words, for that particular part of the discrete spectrum that are associated to unipotent A parameters, she has an independent way of constructing them and analyzing them. Okay? And maybe even having an idea of what the multiplicity formula for that near equivalence class is. Because these are very degenerate parameters, so you might imagine you have some independent way of constructing them. Okay? So this she had that, and now she turned the table around. She used that to show that this gives the right thing locally. Okay? She turned the table around. She used that knowledge of the global knowledge that she has, independently of the trace formula, to show that the local packet is the right one. So that's how she showed it. So she bypassed this question of how character identities. Because in some sense, there are two ways of characterizing this packet, right? One is by these local character identities, and the other is to show that, you know, they give the right solution to the global problem, at least for the relevant part of the relevant near equivalence class. So that's kind of interesting, because if you think from the point of view of trace formula, of course the trace formula should capture everything. But if you try to analyze it from a spectral point of view, which is the easier part to analyze? The tempered part, corresponding to these tempered or generic A parameters, or the degenerate part? Well, it turns out it's easier to take care of the tempered part, or the generic part. Whereas these very degenerate things, they are kind of a nuisance from the analytic point of view. Okay? But from the point of view of explicit construction, the degenerate ones are the ones that you may have independent ways of constructing. Why? Because they are degenerate, which means that they should somehow be lifted from some small groups. Right? So now you have this independent way of understanding them. And that's what she exploits to deal with the unipotent case. Okay, so that's unipotent. I wouldn't say more beyond this. Right, so we understand this. We say this thing is we understood this by data lifting. We have to appeal to the global multiplicity formula. Okay, then now, suppose you understood this, how do you go from here to there? Yeah, so I mentioned that, for example, there's an overlap of these two guys, right? And the overlap, because you see, this one is less than or equals to 1. So if I simultaneously want to be here and there, it means that I need this part to be not there, and I only have one term here. Okay? The parameter I have is precisely that of the trivial representation, if this character were trivial. Okay? But if it's a quadratic character, it could be a quadratic character, right? Because SO2n plus 1s over the rails is a disconnected Lie group. I mean, it has two components. Okay? So you have a trivial character and a quadratic character. Okay, so, I mean, I don't know how to say this. Let's say one-dimension characters. Okay. It is in here and it's also in there. All right. Now, okay, so now we try to go from this understanding to that one. So how to do that? Well, the point is to take hints from this part, because this is somehow a sub-situation of this. Okay? Right? I mean, we want to, about this containment, we have this containment here, and this is a sub of that, this is a sub of that. So this is a special case of that. Okay? And this special case was, had been studied by Adams and Johnson in the mid-80s, I think, or late 80s. So they are looking at representations with this property, parameters with this property, where there's at most one term here. And they show how this packet, so they define certain packets from one-dimensional representations. Okay, so briefly explain what, so you take the hints from the special case of Adams-Johnson. Okay. So maybe I explain what that is. So you look at Adams-Johnson parameter. SDI. Okay, and there's at most one term here. So let's say it is there. So let's say chi with sine of delta. Delta is 0 or 1. SP. I look at this. This is a representation of the Weil group of R. Now, of course, you can restrict to the Weil group of C across SL2. Okay. And in some sense, nothing will happen. I mean, this part becomes trivial. And this part, it's just that this two-dimension representation breaks up into some character plus the inverse or conjugate or something like that. Because this two-dimension representation is obtained by induction from WC, from a one-dimension character of WC. So when you restrict it back, it breaks into a 2. Okay, now if you look at this parameter, I want to say, it looks like a parameter that, okay, so this factors through a levy, L hat. Let me see if this is actually true. I think I would like to write this. Okay, because if you look at this, right, it factors through the following levy, I in I, right? So what is this levy? It has so it's a product of I in I, GL di, see, cross, so SO, I mean this B is even, right? So let me write 2B, okay? 2B plus 1. I mean SP2B. It factors to this levy. Because here you have in some sense this is row and then this is row 2. Okay. So you see that it factors to this levy. Of course you lose information, but when you restrict a parameter, this is like doing base change from R to C. So if you do a base change from R to C, you get some induced representation from this levy. Okay. So what Adams and Johnson, so what is the, okay, so you know it looks like that over C. So the only missing information is the image of the element J in the Weil group of R. Because Weil group of R is generated by Weil group of C and an extra element J whose order is 4. J squared is minus 1 and so on. That's the only element you have to give. And what this element does is that, so the image of that element J under phi, under psi, is something that normalizes this levy. Because of what the J normalize this group. So you normalize this levy. What it does is that on each of the GL factor, it will act as an outer automorphism. And you will do nothing here, because there's nothing you can do here. Okay, so the okay, so that basically is yeah, and yes, and if you look at what psi is on SL2, it is basically taking SL2 into the principal SL2 of each of these factors. Okay, because you know, you pick the full dimension. Okay, so you have that. So that's what Adams-Johnson parameter looks like. And in fact, they do it in the context of general G, not just classical groups. Okay, you can imagine what the parameter is for general G. So you take your G, you look at G hat, okay? You should consider the L group in general, but you take some levy, okay? And then you are going to send the SL2 in the R2 SL2 into the principal SL2 of this levy. You are going to send WC into the center of this levy. Okay, this is going to give a character of a certain levy subgroup. And then you are going to send J into something which normalizes, something in the normalizer of the levy. Okay? So you can run out this parameter in for general G. It will look like that. For classical group, you can explicate it, you know, as a representation, and it will be something like this. Okay, so so if you take such a thing, so we start with our parameter, it defines this levy, but there's an extra action. Okay, now the action so this L hat, maybe I just say is the L group of some L, some twisted levy L in G. But if I ignore this J, right, this levy, of course this levy gives rise to a levy L in G, a levy defined over the rails, so actually the levy of a parabolic subgroup over the rails. But I have this extra action, okay. Then this thing now looks like an L group, and the action is non-trivial here, so or at least it is non-trivial on the GL factor. It's doing some outer automorphism, okay? So if you look at one of these GLs with this outer automorphism action, this looks like an L group of a unitary group. Okay? And indeed, in this L, will be some unitary group. This other part looks like this. It will be some L group of something like that. Okay? And this something, of course, this is not a Levy subgroup of a parabolic subgroup in G over the rails. But if you base change to C, if you extend scalars to C, of course, it becomes a Levy subgroup. So that's the word twisted just means that it is something that is a Levy subgroup over algebraic closure, but it's defined over the base field, but it's not the Levy of a parabolic defined over the base field. So I think this, okay, anyhow, that's what it is, okay? And now, our parameter takes value in, our parameter, psi, factors through this. Okay? So it gives, if you look at this part, this is, so you can think of it as an A parameter for this group. Okay? But this A parameter is a very special type because, so you can think of psi as A parameter for this L, okay? Because it factors through it. But it's a very simple type, okay? Such that psi restricted to SL2 is just the principal SL2 of L hat. But you know, this type of parameter was what is basically the trivial, correspond to trivial representation. Okay? If you have an A parameter like that, the A parameter of the trivial representation is basically you take the SL2 into the principal SL2. So we already, in other words, we know these are these guys here, okay? So we know what this is. This is the packets. So if you look at the L, right, this is just a one-dimensional characters, chi psi of L. Okay. Now, I'm a vague here because I didn't tell you what this unitary group is, because unitary group, of course, over the rails, they can have signatures. And in fact, you're supposed to take all of the signatures. Okay? You can find these unitary groups inside SO2n plus 1 of basically all possible signatures here. And for each one, you are going to get a one-dimension character. Right, let's do it here. Okay. All right. So now, how do we use this to produce the desired Adams-Johnson packet on G? Okay. So this is how do you go from here to there? Okay. So I'm going to call this different L's. Okay. Maybe I make a remark here before I say, which is that, as I said, I didn't specify the signatures. In fact, I'm going to take all possible ones. Okay, so in fact, for each vowel element, so there's a certain double coset. I didn't say what these things are, but it doesn't matter. Okay, just so you take one of the L's, let's say that, you take a quasi-split one. Something like that. C. Okay, so there's some double coset of our group, so that everyone give me this twisted levy. So I have a family of twisted levy, okay, which basically, as I said, correspond to varying the signatures of these unitary groups. Okay, all of them are isomorphic to this, okay? And on each one of them, I have a one-dimension character, so I will call it W psi. And roughly speaking, I want to induce it to G. Okay? If this were a Levy subgroup of a real parabolic, then I would just do parabolic induction. Okay? But you know, these unitary groups, they are not a Levy subgroup of parabolics over rails. But in the case of real group, there's this notion of cohomological induction. Okay? And that's what they used. Yeah, so this Levy turns out that okay, let me write it first. Where this Q is a data stable parabolic algebra of GC. Okay, so here data is a Cartan involution. Okay, that doesn't matter so much. Okay, so this is cohomological induction. So what is this? It's supposed to be an analog of parabolic induction. Okay, but I think just think about analogy, right? So if you think about finite reductive groups, of course you still have parabolic induction, but you also have this so-called Deligne-Lustig induction that takes precisely a twisted Levy, for example, an anisotropic torus, and define some sort of induction to produce a representation of G. Okay? You can think of this as the analog of that for real groups. Okay? In the case of p-adic groups, you might think that maybe what JKU did for the construction of supercapacitor is some version of this cohomological induction, because he takes as a data, initial data, say a twisted Levy, a sequence of twisted Levy subgroup. Okay, and some representation on it, and then from there you produce supercapacitor representations. You may think that these are sort of in spirit parallel, but of course technically it's because it completely looks different. Okay. Okay, so that's what Adam Johnson did. They considered this, and then they you can define Adam Johnson packet to be precisely this representation. As W runs over this double coset. Okay, and after that they check that they define. What did they do? So they define maps from this to that, okay, and then they verify the usual, let's say usual endoscopic character identities. Okay, so that's what they did. And what Moglen and Renard, actually this is in a paper of Arancibia, Moglen and Renard, what they check is that this Adam Johnson's packet agrees with Arthur. Okay, so what's missing after this? After all, we have a candidate. This is visibly multiplicity free. Okay, that's why it's by inspection. It is multiplicity free, and they already verified this, right? So what remains to be done is to verify the twisted endoscopic character identity, the one that goes to GL. Okay, and yeah, I think that seems to be the main thing they have to prove. Now, so how is the proof? Well, it's based on a certain principle. Well, what is it? Well, we are building this packet from some very simple packets, namely one-dimensional packets, a packet of one-dimensional representations. We understand everything about this, so we want to verify, say, endoscopic character identities for the one that we produce by cohomological induction. So we need to know that, or what the heart of the proof comes down to showing that endoscopic transfer commutes with cohomological induction. I think this principle is for all groups. Yeah, this principle is for all groups. However, in their paper, they only write down for classical groups because, you see, this statement is oversimplified somehow. Because when you do this commuting, you have to add in some extra twists in the cohomological induction. I like to think of it as something like the rectifying character in the p-adic case. I mean, there's some shifting of things. And so they write those down for classical groups because that's what they are verifying, because they're trying to compare with Arthur. But they say that, this will be true in general, it's just they didn't write it in that generality. So, okay, so that is the principle. So now we know from here to here, so here to here is cohomological induction. And in fact, by studying this example, then they do the same here. Okay, so this is by cohomological induction. Because we understand this special case. So what is the general case? What's the difference? The difference is that instead of j equals to 1, the size of j equals to 1, you have many, many more j's, right? But when you look at that, so in other words, instead of having a parameter where it's the principal SL2, you have a parameter with not necessarily principal, you have several blocks, so to speak. Okay. Now that is a unipotent, but that is a unipotent parameter on a smaller SO2b plus 1. Imagine your j is not 1, okay, so you have the I part, okay, something, and then you have the j. Right, so here you could have chi j as bj. So the Adams-Johnson case was when this was size 1. Okay, but now you have many copies, let's say. You have 2 copies. But this is a unipotent parameter, right? So we already understood it with this here. So we can take, instead of the, so on LW, instead of having a one-dimension character, what you have is on the GL factors, you have one-dimension characters, as before. But on the classical group, SO2b plus 1, what you have is that unipotent packet. They could be infinite dimension representations. But you take those and do cohomological induction. And that produces for you the packet. Okay? So that's why I say that the procedure here is the same as here, except that instead of taking one-dimension characters, you are now taking general unipotent representations on the classical group part. On the GL part, you still take one-dimension character. Okay. So that's that. Okay. So to finish up, the remaining step. So again, you see that everything here are multiplicity free. By the way, but you can only go to very regular. The reason is because you need to know what you get. What do we know about this guy? I mean, is it irreducible? Is it unitary? Is it whatever, right? But now, so it turns out that if your character is sufficiently regular, if the things that you're inducing is sufficiently regular, then you have very good control of this. You know it's irreducible, non-zero. You know it is unitary. Okay. But, and that's why you put this very regular, this condition. This condition guarantees that you can control this thing. But if you, now suppose you try to go from here to here, you may still sort of imitate this, okay, but now you don't know how to control this thing. All right, so what is done, the remainder part is to go from here to here, you use this so-called Zuckerman's translation functor. Okay? Because the very regular refers to the fact that the infinitesimal character is in some very positive, very far from war, so to speak. Okay? But there are these translation functors of Zuckerman that allows you to move the infinitesimal character around. Okay? But what you need, but here you are going to hit some walls. Okay? The infinitesimal character will rely on some walls on the wild chamber. And in this step, so, these translation functors are very nice if you are in some positive cone. Okay? Because over there, when you move, it gives equivalence of category from, say, Harris-Chandra module with infinitesimal character lambda to Harris-Chandra modules with infinitesimal character mu. Okay? And these are very simple to define functor. You look at lambda minus mu, suppose that is an integral weight, okay? Then you will take a finite dimensional representation of that weight with the highest weight. You tensor your input with that finite dimensional and project onto the part of it whose infinitesimal character is mu. Okay? And this is equivalence of category if you are away from the walls. But when you approach the wall, so let's say your translation functors start from something in the chamber, open set, to the wall. Then this is not an equivalence anymore. Okay? It's an exact functor, but it may skew things, for example. Okay? So, and this is not fully understood. Okay? And that's why from this step to this, Mogren and Reynard show that you can get a general good packet for a good parameter, for a parameter of good parity from a very regular one. So if you have something which is not very regular, you change those k's to make them very regular. There you have the packet already by cohomological induction. You apply translation functor back, you get something, and they check that this is the right A packet. Okay, so what's the principle involved in that proof? Translation functor commutes with endoscopic transfer. This is a general fact. So they established this. So what is missing is because the translation functor is not necessarily equivalence, it may kill certain things. Right? You start with something non-zero, it may go to zero. So what they don't know, so they haven't fully worked out this part. And as a result, they cannot conclusively say that it is multiplicity free. See, because it's not equivalent, so you may send two things to the same thing, or kill something, send it to zero. Right? So because of that, so this is the only missing part. Right? So they don't know, so we cannot say at the moment that the local A parameters over rails is multiplicity free because of this last part. Okay, thank you.